Here are some properties of logarithms that you will likely have seen in either like an algebra class or a pre-calculus class. Let's use them to take some more derivatives. Example 3 says use the properties of logarithms to find derivatives for y equals the natural log of x times x to the fourth plus 1 to the ninth power. So first, we're going to rewrite this using the product rule. So since there are two things being multiplied, we can separate this out into the natural log of x plus the natural log of x to the fourth plus 1 to the ninth power. And then we can also use the power rule to rewrite that as the natural log of x plus 9 natural log of x to the fourth plus 1, like that. So now that we've expanded our function using the properties of logarithms, now we can go ahead and start taking the derivative. So y prime will equal, the first part is just going to be 1 over x plus 9 times 1 over x to the fourth plus 1 times 4x cubed. So if we clean this up a little bit, we'll have 1 over x plus 36x cubed over x to the fourth plus 1. Part B says f of x is equal to the natural log of the cubed root of x minus 4 over x squared plus 1 raised to the third power. So let's rewrite this using properties of logarithms. First, I will bring the power down. So we have 3 times the natural log of the cubed root of x minus 4 over x squared plus 1, like that. And then from here, we can break this into a subtraction statement using the quotient rule. So we have 3 times the natural log of, and I'm going to rewrite this as x minus 4 to the 1/3 power minus the natural log of x squared plus 1, like that. And I can use the power rule one more time. So I have 3 times 1/3 the natural log of x minus 4 minus the natural log of x squared plus 1. And that makes it a little bit easier for us to take the derivative, because if we didn't do this, we'd have to use a lot of like power rule, chain rule, and quotient rule. And this just makes our life a little bit easier. So let's start taking the derivative. So we have 3 times 1/3 times 1 over x minus 4 minus 1 over x squared plus 1 times 2x, like that. And if I distribute the 3 in, the 3 and the 1/3 will cancel out, and then 3 times 2x would be 6x. So we'll have 1 over x minus 4 minus 6x over x squared plus 1, like that. And you can find a common denominator, or you could just leave it like that. Assume that the average lifespan in years for people born from 1920 and projected to 2020 can be modeled by L of x equals 11.249 plus 14.244 natural log of x, where x is the number of years past 1900. Part A says find the function that models the rate of change of lifespan. So we want to find L prime of x, and that's going to be, this portion's a constant, so if we took the derivative of that, that's going to be 0. And then we have 14.244 times the derivative of the natural log of x, which is 1 over x. So that is just 14.244 over x. That is our derivative function. Part B asks, does L of x have a maximum value for x sub 0? Now, sorry, for x greater than 0. Now, if you look at L prime of x, when x is greater than 0, that value is always going to be positive. So for x greater than 0, L prime of x will always be positive. Let me just explain that really quickly. So the numerator of our derivative is 14.244, which is a positive number. And so if you plug in any number greater than 0 for x, then a positive number divided by positive number will be a positive number. So again, L prime of x will always be positive. This means that L of x is always increasing, and therefore does not have a maximum. Okay, part C says evaluate the limit. So if we take the limit as x goes to infinity of our derivative function, which is 4.244 over x, the numerator of that function is going to stay the same as the denominator gets infinitely large. And so this is going to 0. So that is what the limit equals. And part D says, what do the results from parts B and C tell us about the average lifespan? So the average lifespan is always increasing, but at a slower rate as time goes on.